So we'll start with the process, the limit process. This is the one we like to use. You might disagree with that statement, but that may be because you haven't really tried these kind of functions with the x plus h one. So you don't know yet that you like this one, but just play along at least for now. So I have 1 over x minus 1 over a all over x minus a. Fractions subtracted sounds like a great opportunity to incorporate a common denominator. So limit as x approaches a of a minus x over ax all over x minus a. I'm going to just put that x minus a over a 1, so it makes it a little bit more obvious that it's fraction over a fraction. That way the next step doesn't look like a work of pure black magic. All right, a little keep, change, flip action there. All right, this is an idea that came up 2 classes ago when I was here. So the question was, and I got this from a few people, but I don't think I addressed it with everyone. A minus x, x minus a, what's the relationship there? They're exact opposites of one another. If I take 2 opposite numbers and divide them, the result would always be -1. All right, we know they're opposites because I have a positive a here, but a negative a there. I have a negative x here, but a positive x there. So complete opposites of one another. Opposites divide to -1. You can always test it out with something like, all right, here's 2, the number 2. The opposite of that is -2. If you divide them, what do you get? -1. So any 2 numbers that are opposites of one another would divide to equal -1. All right. That allows you to skip the step of factoring out a GCF and then canceling it. All right, so it's a little bit of a time saver at minimum. So let's go purple for those keeping score at home. So limit as x approaches a of -1 over ax. Now I can apply the limit because the troublemaker's gone. I just said I'm going to apply the limit. Bless you. So why am I writing the word limit? I don't know. -1 over x squared. And so that's my f prime of x. So the parent function has a derivative of -1 over x squared. So then the natural question would be, can I use that information to help me find the derivative of the great-grandson function without doing all this work? Well, I guess we got to do the work at least once in order to get a sense, right? So, bless you. Let's enjoy the process. Limit as x approaches a of 1 over x minus 1 minus 1 over a minus 1 over x minus a. It's through processes that are very similar to this that the folks who actually invented all this stuff actually came up with the shortcut rules that we're going to learn about. All right, so we're learning about them, we're not learning them just yet. All right, so these are the underlying concepts that allow those shortcut rules to work. I almost said shortcut works to rule. I don't know. I don't even know what that would mean. All right, so common denominator. Multiply top and bottom by a minus 1. Multiply top and bottom by x minus 1. I think I like this one over here. So limit as x approaches a of a minus 1 minus parentheses x minus 1. That was a common error that was happening a couple days ago. Maybe not so much anymore, but you never know. Something to keep your eyes open for. a minus 1, x minus 1, all over x minus a. But again, oh, I have the markers open. Put it over a 1 so you can see the fraction over fraction relationship. All right, so clean it up. I'm looking at the limit as x approaches a of a minus x all over. All right, so here's the thing. If we're going to do the process of getting a common denominator, simplifying, and keep changing and flipping, in the keep change flip step, that x minus a over 1 would become a 1 over x minus a. So basically, combine the steps, take the denominator that you have on the top, a minus 1, x minus 1, and just tack on that extra denominator, x minus a. Because that's what keep change flip was going to do anyway, so why not just do it all in one shot? All right? But you don't necessarily recognize that unless you see that this is a fraction over a fraction. All right, same process that I did on the previous question, just we're streamlining it now. And we also know that these are going to cancel to a negative 1. So just working off of what I have here, the only things that remain are this guy and these gentlemen. Instead of just rewriting it for the purpose of just writing the expression without the a minus x and the x minus a, I can just work off of this. I'll do my substitution, apply the limit, replace the a's with x's, or in this case just the a. And I'll have negative 1 over, I'm going to have an x minus 1 and another x minus 1 multiplied. So that's going to go and become, this was g, right? So g prime of x. That'll become our derivative. All right? And you can look structurally, I streamlined it a little bit, so it looks like we did less work, but it's really the same amount of work. But we could have done even less work, in fact, no work, because if you compare the parent function and the grandniece function, the only difference would be I have an x here, I have an x minus 1 there. The only difference in the original function is I had an x here and an x minus 1 there. So there seems to be something to that. Now the question would be, will that work all the time? Can I manipulate this function any way I want and just do the same thing to the derivative function and get the same result? The answer would be, it depends. It depends on how you manipulate it. All right. So let's answer the follow-ups. Relationship between the graphs of f of x and g of x. All right. So that's an important thing, because in order to know under what circumstances this process would apply, I would have to know how f of x and g of x relate to one another. So I would put that in my calculator. So I'm turning off my y4. You turn off a function by hitting enter on the equal sign. On is when it's folded. Off is when it's not folded. Enter does the work. All right. y1, I'm going to put it in as 1 over x. y2, 1 over x minus 1. My calculator isn't color screen, so I want to be able to easily distinguish one graph from the other. So I'll hit enter on the slashy thing. So one will come in regular tracing, the other will become fold. So zoom 6, standard zoom is all we need. Original, extra crystal. All right. So the relationship between the two graphs is translated 1 unit. All right. So they're the same graph, same shape, just one is moved over from the other. The original was the non-bolded one, so it's actually 1 unit to the right, I think. So translated 1 unit to the right. All right, it could have been 10 units to the right, 20 units to the left, whatever. In this case, it's 1 unit to the right because that's what was being subtracted from x. All right, so we have a nice relationship there, which is really good. Here's my original graph, and I'll just put in the new asymptote. Actually, I guess I don't need the arrows on it. Just want the shape, the sense of the shape anyway. So something like that. All right. What we're looking at are two graphs that are identical in every way except one is just a shifted version of the other. All right. So that means that the slope relationships would hold up. All right. If I'm out on one graph, all I have to do is go to the corresponding part of the other graph, and I'll have what I need. All right. So what that's telling me is that if I were to look at, you know what, I'll just do it on the calculator. It'll be easier to show you that way. If I look at, let me do value, second trace value, plug in a, I don't know, a 1, I guess. That puts me right there, okay? It has a y value of 1, but I care about the slope. All right, the idea is that you would want to take note of what the slope looks like at that point. All right, then we find the corresponding value on the other graph. All right, so if I'm going to the other graph, go back to the 1. 1 on the other graph corresponds to a no solution, so that's at the location of the asymptote. Right, if I want to get to the same part of the shifted graph, I don't want to plug in a 1 to my second equation, I want to plug in a 2, because I shifted everything 1 unit to the right. So I do a value of 2. In my first graph, that's at 0.5, but in my second graph, it's at 1. When I plugged in a 1 to the original graph, I got a 1 as a result. When I plugged in a 2 to the original, to the translated graph, I got a 1 as a result. All right, so they're separated by a total of 1 unit. The shape, it's the same shape at that x value, right? So when I'm at 1 for my original graph, I have a slope that looks like it's in the negative direction. It's harder to see, but if I have a 2 in my shifted graph, I'll have the same slope. So that's our justification for why the derivative would work out the way it does. All right, but the key term there is translation. All right, so the relationship between the graphs of the derivatives would be the same. All right, if you have just a translation happening in an original function, its derivative would follow that same translation. I could do it with trig also. You know, like you have something like the sine of x. And how about the sine of x minus pi over 2? So the sine of x minus pi over 2. I'll fold it up. I'll do a zoom trig, zoom 7 and zoom trig. Should familiarize, if you're not there yet, I recommend taking some time and familiarizing yourself with the zoom window, because prior to this course, you may never have known that there was a zoom trig in your calculator. It's a zoom tailored specifically to the parameters associated with trig. So it thinks in terms of pi's rather than whole number of units. All right. So what I get from this, again, the bolded is the translated. If I were to actually mark this up, I would look at this as the starting point for my first graph, and this is the starting point of my second graph, because that's where they correspond to one another. It's the same shape around that point. So whatever the slope is here at 0 for the original graph, that would be the same as the slope over here for the translated graph. That's pi over 2, right? That's based on just general knowledge of trig, but also the scaling of it. So that's telling me that if I shift my trig function pi over 2 units, the derivatives will match up also. All right, so I can really give you a beefy looking trig problem. But if you recognize that it's a translated version of the simpler one, then everything works out. That being said, I haven't showed you how to take the derivative of trig functions yet, so even knowing that it has a parent function of sine doesn't really do much for you at this point, because you don't know how to take the derivative of sine anyway. Calculator does. If I'm just looking for numerical relationships, I can get a number. I could find the derivative at pi over 2 for the second graph, but I think it'd be easier to find the derivative at 0 for the original graph. A nifty trick, bless you. If you haven't explored this yet, again, familiarize yourself with the calculator, but some things aren't as obvious. Math 8 is a good way to get a derivative at a number.
Do you have any tissues?
No, you can go to that. It's a good way to get a derivative of a number if you want to type the function in, but if you already have a graph, hit second trace, go down to option 6, that's dy dx. That's another way of saying derivative. So when I select that, at the top of the screen it says y1 equals sine x. That means that it's applying only to that function. So if a question said find the derivative of that old function, whatever the equation is, in this case it's sine of x minus pi over 2. But if it said find the derivative at x equals pi over 2, I might say, well, I'm just going to look at the sine function and find the derivative at 0 because it's going to give me the same thing. So second trace, again, second trace, option 6, and then it doesn't seem like you can do anything, but at this point you just type in the number at x equals 0, and it'll tell you what the derivative is at that location, right? So this is a good feature because not only does it give us the number, in this case it's trying to tell us 1, but it also points out the location on the graph so you can verify it visually. And at least in that little segment there, we can actually think of that as the equation y equals x. So just going from like here to here roughly, it seems to be following the slopes of y equals x. Later on in more advanced calculus classes, you'll learn about ways that you can change trig functions into algebraic functions, which is really weird to think about because all this time you're like, well, we're learning trig because there's no way you can do it algebraically. There is. The problem is it requires you to know 2 semesters of college level calculus before you can understand how and why it works. But it is pretty interesting stuff. When you get there, you'll know what I'm talking about. Joel Feinschmidt is there right now. Good dude.
Good dude.
All right, so consider when you're dealing with a function that's not a parent function, consider how it relates to that parent function. In this case, I'm manipulating just the x value. Right? So this looks like it's a translated version of f of x. So this is the same as f of x equals root x shifted 2 units which way? Left. I don't know what your experience was like in Algebra 2, but I remember getting a lot of pushback when I would say, all right, here's a parabola. And it wasn't really a lot of pushback. It was like kind of playful pushback where it's like, come on, we really got to learn this? We know the other way. Let's just go with that. But this way is kind of important too. If I tell you that a parabola follows the model of ax squared plus bx plus c, you know, like when you were finding axes of symmetry and stuff like that, that's really awesome. You work off this quadratic formula. Yeah, it's incredibly annoying. Quadratic formula works really well with that. So then after that, it was like, okay, now that you master that, let's learn about this. And you're like, oh, we got to do completing the square. Actually, that might have even been in Algebra 1. We have to do completing the square to get it. It just seems like a production. Like, why do we have to do this? I like it the other way. The reason why you do it with the h's and k's is because any function could be represented in that form. All right, so you can take a linear equation. And write it as f of x equals a times x minus h plus k. so no power there. You could do it with a cubic function. The only difference would be it would be a times x minus h cubed plus k. You can do it with a log function. We'll stick with natural logs for the most part. But you might say a ln x minus h plus k. You can do it with a trig function. And in this case, you could do it with radical functions. All represent different transformations. All right. Sometimes if there's a different a value, if the a value, the coefficient is other than 1, now you're talking dilation. If you're only manipulating the x term, it's a horizontal shift. If you have a different k value, so it's not plus 0, it's plus 2 or something, that's a vertical shift. So basically every type of transformation is in here except for a rotation. All right. So what we want to do is we want to just kind of lock in on the idea that we're working with just a horizontal transformation for now. We'll incorporate vertical transformations, we'll incorporate dilations, but for now it's just a horizontal translation. What that tells me, all of that stuff, is that if I find the limit as x approaches a of this difference quotient, so basically if I find the derivative of this one, that'll go a long way towards telling me what the derivative of this one is. All right. This one's a little funky because you get a couple of different approaches. Instincts might take you in one direction, but then of course, me being who I am, I do it in a completely different way. All right, so you might be thinking conjugate. I'm thinking, why don't we factor that bottom? All right, so factor it as a difference of two squares. So factor it like it's a difference of two squares. So you'd have two binomials multiplied. Difference of two squares have two different signs in the middle, 1 minus 1 plus. And then we take the square root of each term. And that'll get us where we need to go. I like doing it this way as opposed to the other way for two reasons. One, it gets me to the answer quicker. And two, it translates, I got to make 1 plus, I'll do that in a second. The other aspect is that it doesn't just work for difference of perfect squares. It'll work for cubes, it'll work for powers of 4, and so on. Whereas conjugates sometimes will let you down.
You can always use it?
Always. And it's very rare that I say something will always work. Sometimes, or most of the time, it's like, well, will it work all the time? Well, it depends. This time, if you have a sum or difference of radicals, you could always factor it into a difference of cubes, difference of squares, difference of quartics, so roots of 4, however you want to do it. Anyway, once you get down to this step, now it's just a plug and chug kind of deal, and we get f prime of x would be equal to 1 over, well, I'm going to have an x squared and another x squared added together. So I have two of those x squared, root x's that I meant to say. So that's what our derivative would be. Just a question of, okay, well now that I have that, how does that help me get the other guy? And the good news is, it's pretty much going to flat out tell me what the other guy is, because the other one is going to follow the same model, only because it's a horizontal translation. So g prime of x would be 1 over 2 times the root of x plus 2. And I didn't have to do any real work to get it. All right. I did have to make a couple of recognitions. The first and the most important one was, is it a horizontal translation? If it's a horizontal translation, then you're good to go. All right. The second realization was, well, it's not really a realization, it's more like some sort of fact or knowledge or whatever. I did need to find out what the derivative of f of x was, right? As we go forward through the course, some derivatives will just stick out in your mind because we'll do them repeatedly. They go from things that you have to work in order to arrive at to, well, I've done this so many times that I know that the derivative of sine is equal to cosine. Like it just happens, like it's implanted in your memory, you can't even get rid of it even if you try. But this one you may still actually have to work out.
Do you have to rationalize the denominator?
Negatory on the rationalizing. All right, never have to rationalize unless you had a multiple choice question, which you won't. But let's say in a world where we had multiple choice questions, you approached one, you did the work, got an answer, but you had a radical on the bottom, all the choices have radicals on the top, then you want to rationalize to see its equivalent, but that's really the only reason. All right, so relationship between the graph, okay, so not to beat this too much to death, but these are the same as the previous page. Same as, I think it was numbers 3 and 4. All right, so then the question would be, what would be the relationship between the derivatives of parent functions and functions that are translations? All right, specifically left and right, because we all know, hopefully, that you can also shift a graph up and down. So right now it's just left and right. So I'm going to write it in symbolic notation. You could write it in words if you want, but if I have some function f of x, I'll do minus h, minus some value h. Its derivative, it wouldn't be equal. Its derivative would be f of x minus h. So what that means, so to translate that further, we would be, that's the same as f of x going to f prime of x, but then doing the substitution afterwards. It's going to look like I'm writing the exact same thing as above, but it has a different flavor to it. All right. What this is saying is substitute in first, then take the derivative. So basically what we did on the previous page, use the limit process, get the answer, you would get some derivative f prime of x minus h. That would be the same as if you were to take the derivative of the parent function and then do the substitution afterwards. So it's a question of, do I substitute in before or do I substitute in after? I think most people will agree that the tough part of finding a derivative is the finding the derivative part, aka using the limit process. All right, so if I can find the derivative of a simpler function and then make adjustments after the fact, that's always going to be preferred to finding the derivative of some nasty function using the limit process. All right, so that's the moral of the story there.